Well, good morning. My name is John Sylvester, and I'm a Vice Provost for Scholarly Technology at the University of Southern California. And I'm chair of the Corporation for Educational Network Initiatives in California, and also a member of the National Lambda Rail Board of Directors. And I'm making this presentation to you today to talk a little bit about the National Lambda Rail, which is a fiber-based research infrastructure. Unfortunately, I'm having to tape this presentation in Los Angeles. I had great intentions to come and be with you all in Rhodes, but unfortunately I got delayed and was unable to leave Los Angeles to be with you there today. So we thought we'd take advantage.
Hello, hello. Alto, sit down. Sit down.
Good morning and welcome everybody to the our first parallel session we're going to have today and Tuesday. Well, as I told to one of our speakers, I would like to be very brief, just to tell you that this, as we have been hearing in the previous session, the internet is unsafe at any level. So, well, attacks, threats, the internet is full of things like other materials in that, as they says, happens. And well, we have a session dedicated to how to analyze ways of dealing with them. Our first speaker is Jan Meyer, who's working on the SARnet security team, and apart from being convinced that the universe is in beta state, as he said in his presentation at the web, he's one of the main authors of the format for exchange of information about incident between organizations. Well, we'll show you about it. You know.
Diego, where do I find my presentation? Ah. Right. Good morning. I'm going to talk about the incident data exchange format. There's a nice URL on which you can find everything related to the project. Unfortunately, I learned that the data model draft is not reachable at this time, but I'll probably fix the URL after I'm done here. First, I would like to sketch a bit about the problem. As Jaap van Til this morning told you, well, the internet is not really a safe place. I work in a computer security incident response team, and we get to deal with them. They do occur. It can be multiple sorts of incidents. The most frequent ones currently are your last favorite Microsoft infectee thingy, open proxies used to distribute spam, Trojan PCs used to distribute spam, root compromises on Unix boxes, although that starts to happen less frequently, and multi-gigabit denial of services. Multi-gigabit, yes, we have numbers of students who have 100 megabit machines and who don't secure them properly. Add 10 of them together and you get close to 1 gigabit, which they can actually push out. We once had the luxury of tracking their conversation in Hebrew and knowing someone who could translate it. All these security incidents, like the compromised box of your professor or this denial of service that is going on, they do not magically disappear. It requires people to actually do something. These people might be CSIRT capabilities. like the ones I'm from. Most of our big universities currently have their own CSERT capabilities, which makes life a lot easier. System administrators, because they actually have access to, well, what is going on the box. You need data to work with. Requires end users. Yes, your Windows system also needs administration. You could also say that they used to be called system administrators, but I wouldn't. And I'm not even talking about management, legal people, police people, the propaganda people. You know, when your company or your site's website says you are owned, you've got a problem. All these technical folks communicate about what happened, where, like what machine, when did it happen, how many days ago, how many months ago, are there still backup tapes on which there is a real good version, how did it happen, because that's what you need to know in order to actually fix the problem so it doesn't happen again 5 minutes after you fixed it. Who did it? In real life it's less interesting. And why? And all this they need to know, except the why part, in order to fix the problem. And get on with whatever the stuff was supposed to be doing in the first place, like serving your web server, giving presentations. This is an example of the stuff that we get in. I kind of anonymized it a bit, but this came in last Saturday. It's the usual email you get. Dear sirs, there's blah-de-blah going on. Occurred then and then. Was from this and this IP address with a domain name. You don't really need that because the resolving, well, it might be dated anyway. Please do blah. Best regards, blah. So what you can see here is that there's a number of data fields, like who is contacting me, so who do I need to send some information back to, what is it about, when did it happen, from where did it come from. What's actually missing in this email is what we call evidence. It's not evidence in the traditional sense that you can use it in a court of law, because that takes a bit more effort. But basically log data showing that, well, yeah, why should we believe this basically anonymous email that's coming in and possibly disconnect the customer. No, let's not do that yet. What would happen then is we put this email into this incident handling system thingy, attach a tracking number to it, and then send off an email to the person responsible for this IP address. I'm fairly certain that the same thing happens in any university site as well. In the end, you get to the person responsible for the box, and you ask him, fix this. And by the way, what happened? And how do you propose to prevent it? So you have this whole chain of people communicating this type of data. So the basic idea was, well, wouldn't it be cool if we would have this format in which we could put all this information, so we do not have to copy and paste it to and from email client systems, blah, blah. Wouldn't it also be cool if it would be unambiguous? So we're all talking about the same thing? Because then, as I'm saying down there all the way, you could do nice things like statistics, maybe predict trends. Like, hey, we're seeing an awful amount of port scans on this port. A couple of years ago, you could be fairly certain that a couple of weeks later, you would see massive amounts of root compromises that use that port. So if you know that up front and you can gather data on a massive scale, you can actually do something with it. So we went about to codify how to say what, when, where, how, why, who. We didn't do the why, actually, because we perceived it to be out of scope. Because, well, if you want to know why someone did something, well, you have to resort to measures that apparently are really in use nowadays in certain countries in this world, but back then they weren't. It should be machine parsable, because then you can, well, slurp a message in, put it into the system. You know the deal. And that way we could automate the load and generalize the automation. Automate the load, yes, there are sites that get 10,000, 20,000, 100,000 reports a week, a day. You can't really do that anymore with copy and paste. And because all these people need to know really a lot about how things happen and why they might happen, they're quite expensive, so you really can't scale that up. The whole corporate background thingy shouldn't be there, but I'm afraid my OpenOffice to PowerPoint export kind of failed. This is an example of an IODEF message. What we basically did was create IODEF XML. This is a message in the format as it is now. It's quite complex, unfortunately. This is actually a live message. You can clearly see that there's some things about the context, when things happened, what was going on, and that was enough of that. So how did this whole IODEF thing came to be? It started out in 1999, yes, almost 5 years ago, well actually 5 years ago, as an IODEF working group in the Trainer Task Force TFC cert. In 2001, we had a requirements draft for it, a requirements RFC informational actually. What we did was basically get the IDMEF approach, the intrusion detection message format, and apply that to the whole incident data exchange problem. They did a requirements draft. Well, yeah, it sounded like a good idea. Let's do a requirements draft. Then we invested some energy into establishing an IETF working group. And then we redid the requirements draft. Anyway, lots of politics involved in standardization, unfortunately. In 2003, something working was going to show up. We got to libIH, which is part of the CertCC project, AirCert. CertCC is nowadays called US Cert, but back then they were still Cert for the whole of the internet. They developed a thing called AirCert to specifically exchange detailed incident information, but they had an advantage in that they controlled both endpoints. The eCcert.net project did not control all the endpoints. This was a project of about 10 C-certs in Europe, and they sat together and tried to solve a couple of common problems, one of which was, well, let's start exchanging incident data using this common format. In that project, we kind of discovered that it really wasn't all that easy, unfortunately, because it turned out that all the incident handling systems that people were happily using did not have all these fields that we expected they would have or they would get. It turned out that, well, yeah, it might be really easy to actually implement those fields into your system, but no one is going to fill that out because it's too much work. So we did get to this nice piece of data format, which everyone felt that, well, yeah, this should do the trick. And then it turns out that, well, yeah, but the source of the data, it's just not there. So we learned a couple of valuable lessons over there. And people in Asia Pacific are also attempting, not really attempting, doing it, implementing IODEF. I think in Korea they're using it for their early warning-ish system. The term early warning system is highly overrated, but I can explain. Slammer, it was, what, 15 minutes before 95% of the vulnerable hosts were infected? Yeah, much good. It will do you to have an early warning of 1 minute for that. In 2004, currently, there's a kind of simplification drive, because as I said, the data model is way too complex. I haven't showed it, because I didn't want to scare you away. It is huge, and it wouldn't fit on one sheet anyway. So people are looking into simplifying it. RID, that's the real-time denial of service dealing with it protocol. I forgot the correct abbreviation. That should be some sort of extension to the base IODEF data model. And we have identified a need for an exchange protocol in INCH. Unfortunately, the deadlines in the INCH working group have the tendency to shift to the future. As you can see, it already started in 2002, and nothing really working has yet come out of that. large and complex, which leads to ambiguous. It's like LDAP. Hey, I've got this big hammer. I can put anything under there that I basically want. People have used it for vulnerability data exchange, early warnings, whatever. But I still cannot really exchange data in the email message I showed earlier on. And that is in fact what I wanted in the first place. In EC-Cert we learned that you need profiling to use it, as in big data model, subset, definition defining the subset, which immediately identifies the whole. Right. No, someone phoned me. Which shows the dangers of not having a watch and relying on technology.
You know, incidents happen. So
Yeah. Good, that still works. Interesting. Which gives me a chance to look back at this, and it's like, well, this is a very simple email. Now, what I actually want is a data model that allows me to put this very simple email into the fields that I have. And currently, IODEF doesn't have that. And if you look at the people developing it, they're coming from all sorts of different backgrounds. CertCC has a way different operational model than most of the NREN C-certs have and most of the university C-certs have. They have this really long-lasting outlook on, well, maybe the internet should be safe in 10 years. We have this kind of pressing problem of, hey, we're seeing thousands of incidents a month and we need to do something like now. And someone, unfortunately, years ago, but that's how people learn, already said it looks really over-engineered. It is. It doesn't yet make daily life really easier. But lessons learned, and life goes on. Inch will still continue, although I will not be dedicating that much energy to it anymore. The other people will. I have no idea what's going to come out of that. As I said, deadlines in Inch have the tendency to be moved forward. Yet there seems to be some interesting progress. Within the TFC cert, we will start experimenting with nice building blocks, maybe using IODEF, maybe not. We'll just be looking at things that will make life in general easier for people handling security incidents. We will, of course, have a look at what Inch is doing. And we will actually have a look at the real problem that we want to solve. Going back to that original email, what's in there, who are the people we're talking to. And in the end, it might actually turn out that we are going to look at IODEF. I think I stayed exactly within the time. Now, I realize that this is a really short introduction into a really complex subject. So if there's any questions, I will be happy to oblige. even, well, might only not work because we've seen all these different types of C-certs popping up. An NREN C-cert does something fundamentally different from, say, Boeing cert or Siemens cert or your average governmental cert.
Okay. In fact, our experience in Spain regarding this is that we had tried to make a group of C-certs of different providers, commercial ones. And well, theoretically, they are pretty much interested on this fourth, because also they want some signal from maybe from the academic community in order to exchange data and make things. I think they see us as a most sort of a neutral player in the internet game. Okay, some other question to Jan?
Well, one last comment on the last comment. We still have the basic problem that people have systems to automate the whole process, and those systems really do not have a consistent set of data fields, which is a very mundane, practical problem. But so far, we've not really been able to convince people to actually use that. So we probably need to get back to the people that originally report stuff and start the chain of automation there.
Okay, just thank Jan for the presentation. Well, our next speaker is Luca Deri, which is working both in the University of Pisa, where he's a lecturer of computer science, and in a company called Neticos. And he's going to present a new format for flow analysis, which is one of the main tools we have for detecting attack threats and all that.
Control? Okay.
Somebody told me about that.
Okay. Good morning. The idea today is to present you something I have done last year, basically in the last 12 months. The idea was the following: to have the ability to monitor IPv4 and IPv6 networks, and to see whether we can do something better than what the technology provided us at the time. Some of you probably know that there is a standard activity named IPFix that is pretending to present and to create a new flow format that allows flow monitoring in modern networks. This work started as a proposal for the IETF for giving them input about new requirements. And unfortunately, the IETF has decided to use Cisco NetFlow as the standard for IPFix. And I will show you basically IPFix's NetFlow without the word Cisco with the IETF name in front. So I somehow tried to take the ideas I put into this work and to put them in practice in an open source software that you can use for monitoring your networks. And because even here, many people are discussing about fast networks, another problem of flow monitoring is that even if you have a very fast router, you cannot really monitor the network at high speed. Yesterday we have seen a presentation from Juniper Networks. They said they have very fast terminal peaks and so on, but those cars are able to operate the maximum at 250,000 packets per second. If you look at Cisco, they have the same problem. They are much slower, 170,000 packets per second using a custom peak that costs $46,000, the peak only. So the last part of the talk, I will show you how to do flow monitoring at higher speed using a commodity PC. Namely, you go to a shop, you buy a Pentium 4 something PC, you buy a normal gigabit card, you put it on, you install Linux, and you're done. Okay, let's start from the beginning. Why passive traffic monitoring? Okay, traffic monitoring is basically an activity based on packet sniffing. Namely, you have a network adapter, you receive the packets, you analyze the packets, you classify them, and you produce traffic reports. If you have a router, okay, you definitely do this into the router. But you can have two kinds of probes. One that is embedded in the router and one that is outside of the router. I'm now talking about the second case. Why traffic monitoring is important? First of all, because the first thing that somebody wants to do is traffic accounting, to know how a certain network it is used, and who is using the network, what protocols are running into the network, and so on. Because it is very simple to have aggregated data. You know that SNMP is out since many years. You can very easily read the counters on the interface. But you don't know who's using this network. So the problem is, I know that my network is overused, or I would like to know more, but I cannot do that with SNMP. So we are trying to do passive monitoring even for this practical problem. Second, you want to do billing, because sometimes you have to charge somebody for using the network in a certain way. You know that every internet ISP has certain peering contracts. And then it is cheap to send traffic to a peer. It is not really cheap to send traffic to somebody that is not really a peer. So we must be careful with that. Also, we want to somehow to detect some security problems. And security somehow is different according to who you are. If you are an end user, you probably care about your PC. You don't want to have a virus. You don't want to use the network for infecting other people. If you are a carrier, you're interested in other kind of problems. For instance, you want to know whether there is somebody in your network that is creating troubles to the whole community, like denial of service or these kind of things. So you want to know and you want to isolate these kind of problems, because a carrier should not go into the problem too deeply. It cannot say, I've seen somebody sent an email with a virus attached to it, so I will prevent this guy from using the net. This is not the case. But a carrier should not allow people to break the network because they have a security problem. So this is also an important issue. So Cisco NetFlow, what is this? It's basically an open standard, open not in the sense that it has been defined by the IETF, also, as I said, IPFix it will be. It's open in the sense that the standard is open. Namely, there is a document from Cisco. You can read it, you can download it, you can implement it. Okay, it's not that Cisco requires you, to pay certain fee for using it. And a flow is basically a set of packets with the same protocol. Protocol mean UDP, ICMP, and so on. The same source and destination, and often using the same port. So it's a set of packets with the very same property. Okay, and together with Harmon and probably RedIRIS, is one of the most important protocol for traffic accounting. Very, very simple. And the NetFlow is based on a client-server architecture. So basically, usually the router sends flows towards one or more collectors. They collect the flows. Usually they save them into a database, and they produce reports, probably using data mining programs. So therefore, it's really a client server. It's the router that decides when to send a flow. And the state of the art of NetFlow is NetFlow version 9 that is currently supported in beta version in some iOS, selected iOS versions. As far as I know, it's not supported by anybody else, other manufacturer. And it's very different from the previous versions. It is different in the sense that Cisco defined a new version every time they wanted to add something. Okay? Whereas in this case, with version 9, they said it's time to define a template. So before sending out the flows, the probe sends a template where it says, okay, your flows will look like this. Okay? And then, of course, it will also send the data flow set, so the real flows. And periodically, this template is sent again. And it's also possible to add new template fields for adding information that is not defined by Cisco. And it's supported, as I said, only in the latest iOS versions and includes support for MPLS IPv6. So if you want to do IPv6 monitoring, NetFlow version 9 is the only way to do that. Huh? And IPv6, in a nutshell, is basically a standard NetFlow. Okay? They have taken and evaluated several flow tools, and they decided that NetFlow version 9 was the way to go. And basically, there is an ability to define new fields in a very standard way. Okay, so you basically specify an IOD object identifier like SNMP is doing. And this protocol is based on a new transport protocol named SCTP, Stream Control Transport Protocol. That is a sort of mixture between UDP and TCP. Okay, so you have the concept of connection, okay, like TCP, but you don't have all the problems of TCP, namely, or features, I would say. So, namely, if somebody goes down, it's not that the sender is stopped, and the sender doesn't have to open the connection if the connection goes down, but the protocol stack continues to send packets until the connection is restored. And there is no very strong flow control. So you basically have a sort of connection-oriented UDP, okay, but that is not using TCP. And this is very good stuff. This, believe me, you have to look at this protocol, so if you're sending data out using UDP, you should really think of using a CDP. The current status is a draft protocol implementation, and basically the bottom line is NetFlow version 9 plus SCTP. So, flow monitoring. Basically, the idea where I started from was to collect a sort of set of requirements, okay, from, and to try to implement them. And I have developed an open source application named NTOP over the past years. So I have a quite large community of people that are using. So I start asking questions to people, what do you really would like to see? And this is basically what I received. So first of all, they want to have a custom flow definition. So they want to say, I want to define my flow the way I like. And they want to add new fields, like, I don't know, for instance, in NetFlow, you don't have anything that is below IP. So for instance, you don't have concept of MAC address. But in many cases, for instance, for security problems, especially in LAN, you're interested in seeing MAC addresses, whether you want to see whether somebody uses spoof addresses. So the ability to do this. A real open flow specification. As I said, IPFix is not really open. They basically taken the flow format produced by the largest networking company in the world and then adopt it. And also the ability to provide payload access. Inside the IETF, there are two groups. One is named IPFix, the other one is called PSAMP. Okay, that among the other things is supposed to talk about payload access. But unfortunately, IPFix does not have access to the payload. So you don't really know what you are transmitting. And you know better than me that the modern protocol don't have the association, a static association between protocol and port. Most of the traffic in your network is a client-to-client traffic. Okay, that many people say, okay, this is peer-to-peer, but it's not really sure that it's peer-to-peer. So you would like to go into the flow and say, what is this? No repudiation. For instance, if you want to do billing, you cannot simply accept flows from a peer. You know better than me that UDP is not really a trusted protocol. Okay? So you cannot really say, like Cisco guys are doing, I send you this flow, and this flow said that Lucas downloaded a gigabyte of a film. Okay, he has to pay for a gigabyte of traffic. It's not the way to go, because there is not security. Whereas my user said, we need no repudiation, so just put a simple digest with a shell key, something simple like that. So I also add information about, for instance, about VLANs. because in modern network you have VLAN, so you should also see this kind of information in addition to MPLS and IPv6. Also, something very cheap for a passive monitoring tool is network and application performance. You don't have to do a ping to know what is the network latency. Okay? You know better than me that if you look at the three-way handshake of TCP, you can measure this information in reality without having to inject traffic on the network. So why can't we do that for free in a flow and put an additional field with this kind of information? As I said, you don't have to compute it. You simply have to do time, three-way handshake, time, difference, and that's it. Also support for connection-oriented or connectionless transport. This has been addressed with SCTP. And of course, think about flow encryption, but flow encryption without imposing to people to use a specified transport. For instance, SCTP has the ability to be sent encrypted, okay? But unfortunately, using IPsec, that it is good, it is safe, it is whatever you want, but it's far too complicated. For instance, Juniper Network have introduced something called XML script. So basically, you have the ability to monitor your network using XML. And they said the transport must be, I don't know, open. Okay, you can use SSH, SSL, whatever you want for that. And of course, the ability to have a MAC information. So basically, I defined a new flow protocol that basically contains everything. And it also contains something called flow compression. So namely, the flows are compressed on the fly using gzip, okay? The same protocol used by gzip, that is an RFC, it's a standard. And of course, you can have payload and fragment information. Also, fragment is another important issue when you want to see whether there is a security problem or a configuration problem, of course. And network performance. So the main benefits are that there are no flow templates. So you don't have the concept of template and the concept of data and the concept that this template can change over the time, because this is an issue. For instance, if you have a collector that is receiving flows from many routers, the very same template ID can have a totally different meaning in one router or in another router. The second problem, the probe, especially if it's using a connection-oriented protocol like SCTP, has to keep track of those templates. And you cannot decode a flow in the fly unless you have received and decoded the template. Cisco guy said, okay, we send a template and then we send just the flows. And we save space. This is true. But if you use compression, okay, you can save much more space. For instance, with compression, I've been able to reduce the space of at least 50%. Also, you have the ability to have payload access. I will show you why this is interesting. And of course, you have for free the network and the application performance detection. So, just to give you an idea of some application based on this thing. First of all, flow-based IDS. I have released myself a couple of months ago a patch to a popular IDS named Snort. Okay, so if you go on the Snort website, you can download this patch. So you can run Snort or NetFlow. So namely, you can, if you have a Cisco router, a Juniper router, or an extreme network switch, you can say, send these flows to this box where Snort is running, as Snort is analyzing and emitting alarms based on this information. But unfortunately, as I said, NetFlow, the default NetFlow does not have payload access. So you can detect, for instance, port scan, these kind of things, but you cannot detect if somebody is sending you the magic string that will kill your PC. Okay. By the way, this is a starting point. But as I said, with the NFlow, you can do that because you have payload access. Also, you have the ability to measure network performance at low cost without having to inject any traffic and using the very same traffic that is flowing into your network. You have the ability to detect, what protocol over the port 1024 is used. So if you see a connection, and in NFlow you can see the first X bytes of the connection, you can say, okay, this is HTTP, this is Gnutella, this is this is that. You can prevent these people from using that protocol. There is something similar called Cisco NBAR that is doing this, but unfortunately is very heavy. It's running only on some selected router and some selected iOS versions, and it has a strong impact on the CPU performance. And of course, you can have a safer building because your flows are assigned. So you know that the sender is really the one who's allowed to send this information to you. It's not that somebody can inject the flow, and you have to pay for traffic that you have not used. Now the slide is not really great, but anyway, I implemented this NFlow together with NetFlow version 9 and version 5 in a probe application named nprobe that I will show you where you can get it. And the idea is that you have to capture this packet, and you have to move the packet up to the nprobe application and to do something with that. But as I said, if you have a standard PC, you cannot go very fast. Okay, you can capture packet very easily, 100, 200,000 packets per second on fast machine, but that's all. And so I said to myself, okay, flows are nice, but if you cannot measure flow traffic on a fast network, and this is the case today, so they are really useless, I think, right? So my idea was to start with a normal PC, a PC you can buy at a normal shop, okay? You put a gigabit card or 100 megabit if you have 100 megabit network, and to do something that allows you to capture packet at high speed, so analyze flows at high speed. So I basically modified the Linux kernel, and I added a new kind of socket named PF ring that is basically a ring, and modifying the low level of the network kernel, the Linux network kernel. Basically, whenever I receive a packet from the network adapter, this packet is copied immediately into the ring and then discarded. So it's not that the packet has to go up to the user space through the normal Linux path. Like, for instance, you don't have to deal with net filter. You don't care. Okay? We just want to be fast. And this is the speed that I've been able to achieve, as I said, on a very slow Pentium 4 without hyperthreading with €50 Intel gigabit card. So as you can see, with very small packets, you can analyze at net flow speed 376,000 packets. As I said, the best that Juniper can offer you for $46,000 is 250,000 packets per second. The best that Cisco can offer is 170,000 packets per second for net flow analysis. Here, we have almost double, 376. And as I said, you can use a normal PC, a very slow quoted, at least a 1 year old Pentium 4 machine with a normal Ethernet card. So basically, you can have flow information, and you can have flow information at high speed, probably not at 10 gig like everybody is pretending to do these days, but at least at 1 gig with a slow PC, a 32-bit Ethernet interface, this is what you can achieve. If you put a 64-bit Ethernet interface, it's even better. So just to complete, this nFlow, as well as NetFlow version 9 and version 5, is implemented and supported this open source probe named nprobe. And I have put a page that describes nFlow, the flow format. And also, if you want to download the PF ring, not only for high-speed packet capture into the probe, but for all your pickup-based applications, like, TCP dump, snort, whatever, you can go and access the PF ring homepage, download the code, and enjoy. Thank you.
Well, thank you. Luca, do you have any question? Please.
I have a question. I would like to ask how exactly is the process with the M5 signatures working? I mean, you see a packet traversing the... Okay. So the question is, can you describe the process to mark packets or to create an index of MD5 signatures that you're using? How exactly is it accomplished? I mean, do you, when you see a certain source IP address and port, do you mark packets? Do you create an MD5 hash at the moment and then mark all packets and keep an index? How is it working and how well does it scale?
In a specific format, okay? This is usually Cisco NetFlow format, okay? On my case, nFlow. Into this packet, okay, there are 16 bytes, okay, that are used as MD5 signature. So you take the packet, okay, you take the private key, you compute the MD5 signature, and you put into the packet the MD5 digest. The collector does exactly the same, and if the digest is the same, so it means that it has not been changed by anybody on the way to you. So it's not that I compute the MD5 on the packets I collect. It's just a way to have a safe channel between the sender and the receiver.
Any other question? Well, it's just last opportunity. Good. If you don't mind.
So how do you see this scale to the core networks or to the backbones rather than to the end network where you have just one ingress point to the network? Both in terms of the number of flows you'll be collecting and correlation between them, as well as the hardware you need to perform that task.
My idea is that flow tools are interesting, flow tools are good, but flow tools have to be used for a specific problem. Namely, you cannot use flow tools for everything. For instance, think about this word. Okay, you have a faster network, so you need a faster probe, then you need a faster collector. Okay, faster, faster, faster. And there is a problem. There is a Cisco router, the very latest and newest one that is shown in the other room. This one is running at 90 terabit per second. So you cannot cope at wide speed. Okay, if you pretend to have a PC with a custom card, with whatever you want, and you pretend to run as fast as the network, you are doing something that's very silly, because there is no way to do that. Period. So the speed of the network will increase much faster than the speed of the PC. And this is, I think this new router is the proof. So the idea is to use these flow tools for what they are good. So namely, if you want to do billing or something in a very specific area, go ahead. If you want to monitor at very high speed, you need a different technology, a different idea. For instance, S-Flow, that is another flow format defined by a company in Mon, it's an RFC. This one is good. Or because this kind of tools, they're very precise. They can tell you everything. They can tell you even the payload. But you cannot pretend to have a PC or something that is as fast as the network, unless you do this into the router. But the router makers, the router manufacturers, will never do this, because they want to use their CPU on the router for switching packets, not for accounting them. It's very simple for them to tell you how many packets a certain router has seen, because they simply have to read a memory address into the CPU. But if you have to compute something like this, or even something simpler, so something that has to take some energy out of the CPU, it is not really possible. So there are problems with the different ingress point, and there are problems with speed. So this is a step ahead, I think. But it has to be used for what it is good for, not for everything.
Anything else? We have time for another question. Latecomers. Okay. Let's thank Luke again for his presentation. Well, next speaker, I think it's an excellent wrap-up of what we have been seeing today in this session. It's Fanan Jahanian, it's founder and chairman of a company called Arbor Networks, and is also professor at the University of Michigan. Has a pretty wide experience on handling with security and dependable systems. So, and he will show us about the ecology of the threats.
Thank you very much, Diego. A pleasure to be here. Over the next 25, 30 minutes, I hope to share with you some, the first speaker, Jan, decided not to scare you. So I'll try to scare you a little bit at the beginning and hopefully talk about some challenges. Don't necessarily have all the solutions, but I can start at least talking about some challenges. This work came out of some of the research that we had done at the University of Michigan, which part of it was commercialized by Arbor Networks, but much of the stuff that I'm talking about today is actually done in public domain in university setting. So, some of the emerging trends as far as security of large networks are concerned. What we're seeing today increasingly is that these threats are globally scoped. They respect no geographical boundary or topological boundaries. They're exceptionally virulent. By that I mean they propagate through the entire population of the Internet in a matter of minutes, as it was alluded to earlier by one of the speakers. Also, we're increasingly dealing with zero-day threats. By that I mean exploiting vulnerabilities for which no signature has been developed. So your IDS boxes or your antivirus solutions that you have don't have the signature of these zero-day threats. Just to give you some anecdotal evidence of some of the kind of attacks, and we deal quite a bit with service providers, large networks. One service provider, for example, experienced over 1,100 denial of service attacks in the first half of 2003. This was based on a presentation by Rob Thomas at NANOG 28. I won't go through the whole list, but again, the first speaker talked about multi-gigabyte attacks, which absolutely is true. It is being seen more and more commonly. In fact, recorded evidence of 10 gigabyte aggregate capacity attacks. Moving down, for example, we have evidence of massive pool of zombies, IRC botnets with over 140,000 machines estimated, which is a pretty awesome force given the current capacity of the network that we have. In fact, with so much capacity, spoofing is no longer cool. 2-3 years ago, it was cool to spoof. Now, real hackers don't actually even spoof. They don't need to. And in fact, we collected some data, and I'll share some of that with you later, that during the peak of NIMDA, during the infection peak of NIMDA a couple of summers ago, we were seeing over 5 billion infection attempts per day, which is pretty phenomenal. Here's a slide actually from some of the colleagues at UCSD. The Slammer attack, actually we referred to it earlier in the talk, that at the beginning, of course, 0 hosts were infected. 75,000 hosts were estimated to have been infected in the first 30 minutes. Infection doubled every 8.5 seconds. Just imagine that, how fast this was propagating. And furthermore, what we saw in case of Slammer is that it was 100 times faster than Code Red in terms of the infection rate. And at peak, there were about 55 million scans per second during the initial, essentially, phase of Slammer. That was, of course, about a year or so ago. The impact of that on the network, what's interesting about Slammer, using this as an example, is that Slammer had no denial of service payload. However, it was propagating so fast such that it manifested itself as a denial of service attack on various routers and the underlying infrastructure of the internet. This is taken from one of the regional service providers with whom we work. And the top graph shows a graph that essentially what you see is the amount of ingress and egress traffic that was seen by those routers. This is taken from Arbor's peak flow device. The amount of traffic change that you see is pretty phenomenal, and it happened almost instantly. That's aggregation of probably 4 or 5 routers at the peering point of this particular service provider. There was also impact on the routing infrastructure, where we have observed, several thousand routes, for example, dropped during that period, primarily because of routers buckling over, mostly /24s and so on. So that's a kind of impact that we're talking about. And if you look at the evolution of network threats over the last, we don't even have to go very far, right? Just go back 2-3 years. What you see is, and I won't go through each of these, I'm sure most of you have experienced some of this in your day-to-day activities. But if you go back to when we started seeing denial of service attacks, the well-known event in February of 2000, where Amazon, CNN, Yahoo, eBay, E-Trade, all were brought down over a couple of days period. What's interesting about these attacks is that these problems manifest themselves nowadays network-wide. If you look at denial of service attacks, if you look at zero-day worms and viruses that we're seeing, worms in particular, that are propagating, and increasingly routing attacks or attacks on the underlying infrastructure are manifesting themselves as network-wide attacks. And our conjecture a few years back when we started this research was that, in fact, increasingly a number of these attacks cannot be solved by the edge customer or edge enterprise, and it really has to be solved by the upstream providers. And the upstream providers have to provide support to the edge customers to be able to essentially, or campus networks, to deal with certain classes of attacks. So I won't have the time to go into a lot of details today about the various sort of solutions based on anomaly detection that we've come up with. What I'm going to talk about really for the next 20 minutes or so is to talk about 2 related projects. One, I'm going to just pick on distributed denial of service attacks as an example and talk about a solution that has gotten quite significant deployment, actually, particularly in North America, now in Europe, across a lot of big networks, particularly service provider networks, for detecting, backtracing, and mitigating denial of service attacks. And there's an implication in terms of how that solution is applicable to other types of attacks. The second part of the talk, I am going to talk about an ongoing research activity with monitoring. Again, if you believe the conjecture that these attacks are increasingly global and network-wide, a research project that we have ongoing looking at black hole monitoring a lot of unused address spaces to characterize, track, monitor, and essentially, hopefully, serve as an early warning system for brewing attacks. So I'm going to split the talk into two parts from moving on and talk about these two related activities. First, with the denial of service attacks. All of you are familiar with it. I don't really need to give a definition of what denial of service attack is, except that massive amount of essentially traffic that's coming that's exhausting some resource, whether it's your network resource, or it's a website that you're getting attacked with just random bogus essentially, or it may be a firewall or a router. Typically, there are two phases to it. There's an initial intrusion where networks are scanned, vulnerable hosts are identified, they're compromised by installing tools and backdoors and so on. The second phase of it is the actual distributed denial of service attack. Sometimes it's spoofed, sometimes it's not, but essentially you signal and launch an attack on a target website or a target enterprise, say Microsoft's backbone, for example. And it could be on routers, DNS infrastructure, and so on. What's interesting as we've watched essentially denial of service attacks, particularly over the past 5 years, is that the distinction between phase 1 and phase 2 is blurring. By that I mean, again, using Slammer, although there was no denial of service payload, because it was moving so fast, it manifested itself as a denial of service attack on a significant number of essentially routing infrastructure of the underlying internet itself. So there are a couple of myths in terms of how you deal with denial of service attacks. And this goes back to 3-4 years ago when we were playing around with this problem. Most of my background in my group has to do really with routing and a routing architecture and so on. And we looked at security from much more of a network operations point of view. One thing that we noticed is that there were a lot of people who talked about these magic boxes that you take and you deploy it in front of whatever is your critical resource. Back then it was the eBay and a Yahoo and a Microsoft website and so on. You put a box, a filtering box in front of it, and I compared that to trying to drink from a fire hose. Essentially the same thing that you can do to a website, you can do to a firewall, you can do it to a router, believe it or not. And in fact, trying to put a box in front of a target often doesn't solve the problem. And in fact, attacks, there's a well-known attack on a very, very large enterprise where there was an attack on an upstream router, and this enterprise has a lot of properties underneath it, and you looked up and there was no traffic coming in. And it looked like there was actually no traffic. Well, what happened is the backbone was seeing no traffic, and upstream a router was attacked, and in fact, the whole network was shut down for some amount of time. The second myth, very briefly, having to do with the use of IDS tools. Essentially, any kind of a signature-based solution does not allow us to deal with denial of service attacks. For certain classes of attacks, it certainly does. But increasingly, the kind of attacks that we're seeing, signature-based solutions are not going to deal with it. Slammer is a good example of that again. So there are also best practices, and I'm not going to argue against best practices. I certainly wouldn't argue against having IDSs deployed in your network. From good computer hygiene to make sure you patch those darn, Windows machine that you have and so on. And the list goes on. And then there's a push, for example, for routing and DNS authentication, the Internet Routing Registry, campus-wide incident response teams. Many of you actually are involved in that. All of that is good. As we experience that every day, that's still probably not enough. So what is the solution? I'm actually not sure what the solution is, but here's a stab at it that has had significant success to deal with certain kinds of attacks. Well, what we did was instead of essentially just relying on signature-based solution. We actually, in addition to the signature-based analysis, for example, you see massive amount of ICMP traffic. We also essentially started relying on network anomaly detection. By that I mean, instead of having operators try to model, trying to model the underlying threat, we argued that operators really should start modeling their network. By anomaly detection, obviously, what I mean is that try to model what's normal for your network, and deviation from your normal behavior should be flagged as potentially malicious traffic. And of course, that's a lot easier said than done, particularly in a large-scale distributed system where you have different sensors sitting in different places, and what does it really mean for a network to be normal? So the peak flow architecture had really several components to it. The idea behind it is that, as I said, we create models of network behavior using essentially two sources of information. Flow statistics, in fact, we use NetFlow, and topology information from the routers themselves. Now, how we get the NetFlow, I'll talk about it some more. We could get it from routers and switches. We could do NetFlow sampling. We also have devices that we ourselves have built that we deploy and generate NetFlow to the back end. And this model of normal traffic, it's really built at different layers in granularity. So I could, for example, model all the traffic that comes in and out of Microsoft's network. I could, for example, model traffic that's coming on a campus network from all the dorms, and which is usually a cesspool of interesting activities, from the dorms, for example, to the rest of the campus or to the internet. So we can create models, very, very sophisticated models, all of their coarse grain at various levels of granularity. We, for example, can create models of traffic in and out of certain routers, say at peering points of British Telecom or AT&T as they cooperate. Then we use signature analysis and dynamic profiling to monitor and detect an all-service attack in a totally distributed fashion in a big network. And again, we're talking about, say, a service provider network. We use some of the distributed event aggregation techniques that we have come up with to not only do the detection, but also to do the back tracing of it. It doesn't mean that every router in your network is instrumented to generate NetFlow. I compare that primarily, for example, to how you ask a kid to connect the dots to draw a picture. Well, it turns out you don't have to connect all the dots. You can connect enough to the dots and say, ha, it's an elephant. It certainly will not be a duck, so it'll be close enough to an elephant, for example. And then we use backtracing to go away from the target. As I said, you may want to do the detection closer to the target, but you may want to do the filtering of it as far away from the target as possible. And then we come up in a semi-automatic fashion with various attack-specific remediation method to minimize the impact on a particular target. Here's an example of how peak flow works. Imagine in this graph, for example, right here, this could be a campus network, this could be Yahoo, this could be Microsoft. This is sort of an edge enterprise. This is your regional provider potentially providing network connectivity. In case of campus network, it could be one of the RME networks that's providing. And then you have your peering points to commercial providers and providing transit. So what we do is we typically sit close to routers, next to routers, and we can essentially get information, a single box to get information from multiple routers, and it's typically routing information, BGP information, plus NetFlow. And the details of it, I'm happy to take that offline with you and send you some information to read the documents. But essentially, you get information from that, and it could be essentially at a peering point where we've actually shown certain levels of NetFlow sampling would also work for these classes of attacks that we're looking at. So we get that information from the routers, and what we're able to do with that is we essentially create this profile of what's normal and what's not normal in the network. And that applies, again, at various levels of granularity in various places in the network as well. So this is normal traffic coming through. Well, it turns out, in this case, that you may actually have a denial of service attack coming in through another peering point or multiple peering points, again, targeted at this particular website. So what we do is we're collecting information now in real time, again from those NetFlow devices. And we're essentially comparing the information that's coming in to the models that we've created. Deviation from normal behavior is signaled as a potential anomaly. Here's a trick. Seeing it exactly in one place may not be enough. So what we're doing is we're essentially in a totally distributed fashion. These collectors, it's a two-level hierarchy. The collectors are collecting information, analyzing it, and potentially flagging anomalous behavior. Then there's a controller that sits in the back So the collectors and the controllers work together, and the collectors are discovering these anomalous events, but the controller essentially is aggregating that information, correlating that information, and by looking at information that's coming from various places, and this was my argument, again, as I highlighted earlier, is that these kinds of attack, just sitting at the edge of your network, well, you see massive amount of traffic coming in. But you get a lot more visibility if you're away from the target, looking at essentially as various routers traffic is coming in. I'm oversimplifying the description to some extent here. So in real time, then, we essentially create what we call is a fingerprint for that attack. That fingerprint for that attack then is used to match against the traffic that's coming in to essentially backtrace it. This is what I mean by connecting the dots. Connecting enough of the dots, going back away from the target to where your peering points are. And our argument was that what you want to do is, for a case like this, is you want to be able to filter this as far away from the target, but wherever is your sphere of control. For example, for the Microsoft network, Microsoft may want to filter it at the peering points where it's receiving connectivity from outside because they have a pretty large backbone. Should not necessarily require cooperation of their upstream provider. So at that point, we also generate essentially various kinds of filters that can be enabled in Cisco, Juniper, Extreme, various kinds of routers or switches, and firewalls, including checkpoints and Cisco's and so on. And those things can be installed manually or automatically. Of course, no one who runs real networks would want to do this automatically, so everybody wants to have some manual intervention. And finally, somehow magically this works and normal traffic resumes to the website. In terms of mitigation strategies, we have a number of things that we sort of observed, from do nothing, which is a very, very popular approach to mitigating traffic, which is do absolutely nothing, and 15 minutes later it goes away. If nobody has complained, you're safe. If somebody has complained, you blame your upstream provider and you're done, right? It's very effective, as it turns out. Or you notify the downstream or upstream provider saying you're under attack, or you tell your upstream provider it's your fault. We also, on a more serious note, use ACLs or firewalls. This is the automatic signatures that we generate. We can also use rate-limiting, technologies to essentially, based on characterization of the traffic itself, to minimize the impact. We also have two other techniques that we apply. We use BGP blackholing, where we black hole the traffic into nowhere. And finally, an increasingly popular approach is sinkholing or off-ramping, where you take some of the traffic, off-ramp it, do analysis, clean it up, and send it back in. And that has become increasingly popular for certain class of traffic in certain kinds of networks, and we're beginning to see that. And we're able essentially to do all of these things, and over time have shown how they can be incorporated. But important thing is here is that the data that's necessary to know which one to choose and how to configure it is really what the quirks of the analysis is itself. I really don't have a lot of time to go through a case study, detailed case study. Just wanted to highlight, in terms of where this project started. It started from a university project, of course, and we used our local research network, which was our upstream provider, namely MishNet, which is run by Merit Network, to deploy the technology. That was about 4 years ago. And over time, it got deployed on Internet 2 and several other academic institutions. But then quickly, it shifted to commercial networks. So what you see, the dots there, are actually Tier 1, Tier 2 transit providers that have actually deployed the technology and are using it today. And there are about 75 of them. Most concentration of course, is in North America. A handful of them, of course, in Europe, and that's growing. Again, the focus hasn't been on the academic networks. It's been actually picked up by most of the commercial networks, and a handful of them in Asia Pacific. The kind of stuff that you see, there's a traffic monitoring piece of it that I haven't even talked about, but essentially this allows you, this is an example of a recent large denial of service attack where anomalies can be classified as low, medium, high. This is your sort of the first knock view of the thing. And then there's a visual breakout of the effective elements in the network itself. Happy to take all of this offline. And then there's additional details that provide it, for example, in terms of the severity, the duration, the direction, specific elements that are impacted and attack on the attack, from the router interface to the source and the destination, to the extent that's possible. For example, you see the output interface, the input interfaces that are impacted, and various sorts of data characteristics that comes with it. a lot of work has gone into essentially defining what this information is, and we relied on a lot of help from network operators actually for this information, what makes sense. And then finally, we'll also present information about the fingerprint of this attack and automatically generate the appropriate, the ACL, CAR, or the firewall rule set for blocking these attacks. Again, I emphasize that we automatically generate it, but it's not necessarily the case that people automatically deploy it. Usually there's some human intervention before some of that gets deployed. So that sort of brings to a closure to the discussion on the denial of service attack. I want to switch gears and talk about the second part of the talk, which has to do with monitoring of unused address spaces. And this is done as a research project in public domain, obviously. So a few years ago, we had access to a contiguous address space of a large /8, of a /8, which was an unused address block. And interestingly enough, and there are a handful of those around. The notion of black hole monitoring, we started looking at this 3 or 4 years ago, and a number of other groups are also looking at it. The idea here is that there are blocks of address spaces that, while they're routable, they actually contain no host in them. And the conjecture we had was that the traffic on these black holes, and it's been proved to be correct, especially during the last couple of years, is that most of the traffic is due to scans, worm propagation, denial of service backscatter. It's essentially either misconfigured route traffic or it's bad stuff. It's just not good stuff because these are black holes. So this is for those of you who are familiar with BGP off-ramping for traffic inspection, very similar idea. So our conjecture was, well, what if we could essentially route this black hole traffic and start looking at it to see what we see? And that was really the idea. So initially passively. So if you take this to an extreme, it could be a full service emulation like a honeypot. Or at the other end of the extreme is just a passive monitor that sits there and sees what kind of a junk that you see on the network itself. That was the idea that we started with. So there are multiple components to this. So going back to this again, you see, for example, that there's a router there and there's a black hole in it. There's information is being routed essentially to our box sitting there and watching this. And I'll talk about how actually we deployed this in a moment. So there are really 3 components to it. There's a passive component, which it measures the traffic, looks for scans, backscatter, and it attempts to quantify the breadth of the worm infections and scope of the denial of service attacks. There's also actually an active component. Our idea was that instead of having a full service emulation of say, whatever is the application, which would have been very costly, like a honeypot, although we can do that, instead of that, what we do is we essentially SYNAC the first packet that we get. And our conjecture was, well, how much information can we get out? It turns out you can find out a lot about an attack if you just SYNAC and that get very first payload. Significant amount of information. It's not complete in a sense that you miss some things. But we were surprised to see how much more information you can get between just doing it passively versus just SYNACing it and getting that very, very first payload. So that was sort of the conjecture. And then there's an alerting module. If, say, there's something interesting going on, we alert somebody. So these were the 3 components. And again, the kind of stuff that we saw are wide-scale port scans and service sweep for attackers. We're able to characterize and quantify internet worm activities. I have an example to show you in the next couple of minutes. And estimating the type and severity of globally scoped denial of service incidents. So we had access to this /8. And it was a joint project by Merit Network, Arbor Networks, and University of Michigan, started in 2001. And as I said, in this case, 10,000 to 100,000, essentially TCP handshakes, we completed it to get that payload. That was the idea. And then we reassembled the worm payload, identified and log each of them, attempted to essentially do an MD5 signature on it, store it someplace, and then do post-analysis of it. And, random scans, DOS, backscatter, and so on was the stuff that we were completing. We were surprised over the year or two that we were essentially collecting data, the amount of information, and a lot of times after a worm hit, we would go back and do post-analysis of it to see what kind of evidence we found in terms of before the outbreak, the scans at outbreak, and so on. And that information, and this is ongoing research, has been actually phenomenal in terms of the insight into some of these worms. Here's an example of it over the next couple of minutes. For example, consider the worm blaster, the blaster worm. And you recall in July 16, there were all sorts of advisories that there is a vulnerability in DCOM RPC services from Microsoft. Great. Well, it turns out a lot of people didn't patch their machines, as you would have expected. Although there were a number of advisories, including from Department of Homeland Security and various organizations globally, by August 11, when the actual worm hit, and then we saw by August 13th, some variant of that worm also appeared. How it spreads, let me not go over it in the interest of time, just to tell you that it wasn't a random essentially scanning. 40% of the time, it was a /24 within your local /16, and 60% of the time was random /24s. So there was some sanity to the madness of this particular worm. The data that I'm going to show you the next 2-3 slides. Do I have a couple of more minutes to go over this? Great. So next 4 or 5 slides is just to tease you, and there's a report that we've written on this. I'm happy to share that with you if you're interested, is the data that we collected from our black hole. So we're just monitoring unused address spaces. For example, this shows 3 phases of this worm's life cycle. There was a growth phase where we just saw a massive suddenly infection taking place. There is a decay phase, which was exponential, and it went down. And there's a persistence part of it. This question always comes up. What you see here, let's refer to it as monitoring measurement issues, which means our thing crashed. So we lost some of that data. Graduate students got into trouble for it, but that's the extent of it. Yeah, as they should, right? There was a minimum doubling of 2.3 hours during a growth phase. Compare this to Slammer, which was 8 or 9 seconds, as estimated. We saw over 286,000 unique IP addresses, some of them potentially from your own networks here, in the black hole. And this was, again, just measurement from a single black hole. Here's the... I'm sorry, I must have, well, I don't have the slide that shows the growth, but we saw significant amount of scans right leading to the infection. It was actually quite surprising to see that there were no scans for this particular port. And the 2 weeks before the actual attack started, we saw a significant amount of scans in our black hole, essentially. And then we saw this huge essentially uptick in the traffic, and then as the providers went ahead and applied ingress and egress filtering, we saw, in fact, an exponential decay of the blaster, where the half-life of it was about 10.4 hours. And you see that very quickly, within about 5 days, call that quickly in internet time, pretty much all of this was cleaned up. In other words, we saw very little traces of the blaster attack. When we did an analysis of the infected hosts, remember, we can sit in our black hole and identify potentially infected hosts that are scanning us. We saw fairly global distribution of these attacks. It was not unique. For example, in the previous attacks, what we've seen is Korea, for example, had a significant number of machines that were compromised for the Slammer attack. In this case, we saw a very, very broad global distribution of it. Second domain analysis is kind of a crude analysis, showed that customer broadband providers were in fact a significant majority of these machines that were compromised. And finally, as I mentioned, we observed over 280,000 unique IP addresses in the black hole displaying essentially blaster behavior. A couple of more interesting observations. Well, what we saw was that this thing pretty much died right around here. Somebody really smart decided to release a good worm to fix the bad worm. Well, this is what the good worm did, which the damage was just as bad as the bad worm itself. And what was interesting is the cyclic behavior that you see. We saw it rise, and the scans go down, go up, and go down, and so on. And we have some conjectures why that's the case. But here's actually the punchline about the attack. And we've seen this actually in case of Code Red and NIMDA and so on. What we're seeing, this goes through October of 2003, but it actually continued all the way through middle of this year, where we actually see about 1,000 machines that are potentially infected, and you see the cyclic behavior just continue. These machines, we suspect these are probably mom and pop operations. They turn on their machines in the morning, they start scanning the universe, they turn them off, they go home, they stop scanning, they come back and turn them on again. So that's our conjecture. If you have any other ideas, love to hear it. I'm just about done. So there are about another 10 or 15 slides related to the blaster and a report on it. If you're interested, happy to share that with you. 2 minutes. I'm almost done. The depth versus breadth classification. As I mentioned, what we went for is we deployed it in a single black hole, but you can see that, in fact, you can deploy this in a lot of black holes. Instead of one large continuous one, you can get a lot of little black holes and get the deployment. The other thing is that we didn't just do passive monitoring. We completed the handshake for some of the TCP connections. You can have actually a much more elaborate service simulation. Turn this into a full service, sort of a honeypot if you wanted to. What we believe, where we pick, is a pretty scalable way of getting some coarse-grained analysis of this data. To wrap up, the project is called Internet Motion Sensor. We're now working about 20 or 30 big organization internet service providers. We're, instead of having us just access at a /8, we're getting a lot of /24, /23, /16s, and we're essentially deploying these boxes there, and they're collecting information. They provide information to the institution that deploys it, but also we take the data, we aggregate it, and provide it back to everyone. This is done all from the University of Michigan. We'll provide it back to everyone who contributes data. So if you're interested in participating in this, in deploying a box, collecting essentially black hole monitoring information, you can collect it, contribute it to our repository, and then you get access also not only to your own data, but also to aggregate information that we're collecting from some of the largest providers in North America and now in Europe and a bunch of big enterprises. So that was sort of the advertising for the research project. If you're interested in participating, let me know. Wrap up. I told you some stories. Hope you enjoyed them. Some information. There are a bunch of white papers and additional research reports that we've written. Some of it comes from Arbor Networks. Some of it comes from University of Michigan. You're welcome to send me email. I'm happy to take this offline with you and send you more information. If you want to know more about denial of service attack, traffic monitoring, and so on, Arbor Networks actually has people in Europe that they can talk to, and they're technical and happy to interact with you on that. I am done for time. Thank you very much.
So we have, well, officially 2 minutes, but I guess a couple of questions, comments.
Yes.
Just a quick information question.
Sure.
Are those papers online? And if so, do I look under arbor.net?
That's a good question. You know, the paper, the last paper, for example, has been submitted. The final version is in ready. I guess some of them are online, but some of them you have to send me email. If you go to Arbor, you would be able to find them. But the research papers, you probably have to. The recent ones, send me email, and I'm happy to follow up with you. Yes, Ken. Good to see you.
Did
I'm not the only token American here. Glad to see you here.
Did any of the ISPs place restrictions on access to the data that they're providing via the motion sensors? Or?
It depends if they told their lawyers or not. That's a good question. It turns out we collect a lot of other information from service providers, like the denial of service attacks that I was talking about. All of that ISPs do not share. It's customer information. They keep it. For the black hole monitoring stuff, because it's essentially a black hole where there should be no real traffic in it, they have no problem sharing that information, which is actually great progress for us. So they have what we're doing is essentially we're aggregating some of the information, we're anonymizing it, but we're sharing it back with the broader community as the interest is there. Thanks for the question. Yes, sir.
But is there no new thread that compute the fact that there are black holes, and so that there are not attacking the black holes networks?
If I understand your question, that's a great question. So if somebody knows you're running a black hole, they attack your black hole and essentially defeat that. I guess that's what you're asking. Is that what you're asking?
Or avoiding those net ranges.
Absolutely, great question. Yes. So if it was the /8 and somebody knows multiple monitoring stuff in that stack that they avoided. The whole purpose of actually going with this distributed model is the Internet Motion Sensor distributed model is we want to have many, many black holes so that in fact you get a broad coverage, and we also have come up with some ideas of moving things around and so on dynamically to avoid detection. But the whole idea here being is essentially by having many, many of these, small and medium and large, and this is an ongoing research, we do have seen already that having access to a big range gives you some visibility. But having access to a lot of little black holes gives you totally different visibility about the network. So it's still evolving. That's a good question. Yes?
What's the smallest size?
I guess the single machine.
That's still useful.
Not really. 24 is nice. Getting access to a 24 is nice. If we have a bunch of 24s and 16s, then I think a lot of single /32s will probably be free. But it has to complement the 24s.
Any other question? Well, I would like to thank all the speakers because punctuality is one of the main virtues of a gentleman, and you have behaved a really gentleman. Thank you, Fanem, and you all. Okay.